Okay, good morning, everyone. Let's get started. Today marks not the end, but the end of the beginning. Undergrads, you're submitting A10 by 11:59 p.m. tonight. Grads, you're submitting the fifth and final differentiable assignment by 11:59 p.m. tonight. All of you should now have a firm, solid, reliable foundation upon which you can design, formulate, describe to us, and then execute an evolutionary robotics experiment of your own devising or picking a version of something we've come up with before. So we're going to talk about the final project. We're going to spend a few minutes talking about the final project now and then get back to lecture. Any questions about the finality of the assignments? Okay. All right, let's talk about the final project. I will post I will post the instructions about the final project on Brightspace when I get back to my office after lecture. I'm going to post this document, and please bear with me. We're going to walk through this together just so we're all on the same page about expectations for the final project. All right, so here we go. You will probably have seen in the subreddit, there is already at the end of all of the learning modules a pointer to a bunch of final project ideas. For the undergraduates, you can choose if you want anything from that list. There are some that are listed as easy projects, some that are listed as hard projects, or you can devise a final project of your own. Okay. Those taking the course for graduate credit, you must come up with an idea of your own. If you do, undergrad or grad, if you choose your own idea, it must involve modifying the code base developed during A1 through A10 or D1 through D5. So for the grad students, you can choose to go back to the non-differentiable assignments to build your final project on, or you can use the differentiable simulator. But I don't want folks throwing away everything you've built and starting from scratch. First of all, there just isn't enough time left in the semester to do something cool. So you've got to use one of these two foundations, either the A's or the D's. Okay. I put up some final project ideas for those that want to use the differentiable assignment code base here. Again, for the grads, I'd like you to try and devise something of your own. Okay, so there are 4 weeks remaining in the semester. You're going to use this time to devise and implement incrementally, being the important word here, your final project. I don't know about you, but when I was a student, I often thought the best thing to do was leave things to the last minute, stay up all night and code up your final project. As you're about to see, there are many checks and balances in place here to ensure that you don't choose that path. Okay. If you found that the programming assignments were somewhat challenging, I would suggest choosing one of the easy projects. Obviously, if you'd like to try something more challenging, choose something from the hard list. Importantly, no one will be penalized for choosing an easy project. I want all of you to be able to choose something that's at or a little bit beyond your ability, so that you find you're working on something that's fun and challenging, and you have something interesting to show us at the end of the semester. Okay. Very importantly, if you want to try an idea of your own, I would suggest emailing the TA or me. Come and see the TA or myself during our office hours between now and next Tuesday to try out your idea. You're all becoming robotics experts, but you're still probably not that great at being able to estimate what kind of projects are doable given your ability over the next 4 weeks. So now is the time. Over the next week, find a way to connect with the TA or myself and say, here's an idea, and we will send you back, we will give you some feedback. That's probably too easy, that's too hard. Sounds great, it's a good idea. Why don't you break it down in these ways and try these baby steps first and work towards your final project idea, and so on. What we want to try and guard against, or what all of us are going to try and do over the next week, is make sure that you don't devise something that's ambitious and have no real baby steps or incremental steps to get there. I don't want anyone sort of crossing their fingers, having their code base crashing for the next 3.5 weeks, and hoping by the final 4th week you get something working. Okay. So we will help you try and verify whether we think it's doable in the remaining time. Okay, so in order to do this, what you are going to be doing between now and next Tuesday is thinking and possibly coding up a prototype or playing around a little bit with your code base to break down your idea into 4 weekly milestones. We're going to keep with the cadence that we've established in this course, where every Tuesday night you are now going to be submitting a weekly milestone, demonstrating to us that you've reached that milestone. You've broken your final idea down into 4 bits, and you're going to implement each of those 4 bits week by week. Okay. So I want you to think about how to break things down into 4 digestible bits. And then also for each one of those 4 increments, I want you to think about how you would demonstrate to us that you've successfully implemented that increment, surprise, surprise, using an image or 2 or a short video. So from the perspective of the TA and myself, when we go and grade your weekly deliverables, they're going to look to us very much like your submissions of the assignments and the differentiable assignments. We want you to show us and not tell us that things are working. There's 59 students in this class. We don't have time to read detailed weekly reports from everyone about how everything is going. What you're going to be submitting is a sentence or 2 saying, just to remind you, I'm working towards this final project, and my goal for this week was to get this working. Here you can see this mechanism working in these images or figures or plots or 10 or 20 second video. Okay. So I then want you, once you've thought this all out, I want you to write out these milestones. It doesn't have to be an essay. 2 or 3 sentences for each of the 4 milestones is enough. And write out 1 or 2 sentences about how you plan to visualize the completion of that milestone. So a few sentences for each of these weekly deliverables. So just to give you a sense for how this would be, let's take a hypothetical student who's proposing to implement the Up, Up, and Away project. So you'll see that all the final project ideas listed in the subreddit have cutesy names. The Up, Up, and Away project is getting your robot to jump up and stay in the air for as long as possible, which possibly sounds like not a very difficult thing to do, but it turns out that jumping is very susceptible to perverse instantiation. And as you're going to see in a moment, this hypothetical student has tried to think ahead about what those possible perverse instantiations might be, and part of their milestones are going to be demonstrations about how to snuff out those perverse instantiations, and at the end, get what they want, which is a robot that can jump up, up, and away. Okay, so this is the student writing this out. I would like, and talking to the TA and myself, I would like to implement the Up, Up, and Away project to make my robot jump. To do so, I'm going to modify simulate.py so that when the simulation ends, it writes out all the touch sensor values in the binary matrix for all time steps rather than the distance that the robot traveled. So if we're going to now get a robot that jumps rather than walks, one of the things we're going to have to change is the fitness function, right? We're no longer going to select for how far to the right the robot moves. For this student, they're starting to tie jumping to touch values in the feet, which kind of makes sense. What's the intuition here?
For like a period of time, have no sensors on for as long as possible.
So for some period of time, the student is probably going to construct a fitness function that looks for contiguous periods of time for which all the touch sensors are not firing. The robot is off the ground. Okay. I'll include a screenshot of simulate.py writing out this matrix. So they're showing a screenshot not of the code, but of their code doing something, writing out this matrix and them opening that file and showing a binary matrix. So they're going to demonstrate to us that first step. Okay, so the first milestone is exactly this 2 or 3 sentences, which this hypothetical student would submit this coming Tuesday by 11:59 p.m. This is the plan. Okay. The following week, the following week they're going to propose the second milestone, which is in the second week they're going to modify search.py. They're now going to modify the evolutionary algorithm to read in the binary matrix, and compute fitness is the number of -1. So the number of touch sensors and the number of time steps for which touch sensors are not firing. So they're going to try and minimize touch information, stay off the ground for as long as possible. This will lead to the evolution of robots that keep as many feet off the ground as possible, which I will show with the video. So this is what they're proposing to do by the end of week 2. The end of week 3, they're proposing to modify the fitness function to compute the number of consecutive time steps the robot keeps all feet off the ground. So this is a simpler thing to do, but it's implicit in what this hypothetical student is saying, that they know this is probably going to lead to perverse instantiation. This is not going to lead to jumping. This is going to lead to tap dancing, right? The robot's going to try and keep as few feet off the ground as possible, or minimize the number of contacts as possible. Okay. So they're proposing to modify the fitness function to compute the number of consecutive time steps the robot keeps all feet off the ground. I will demonstrate this with a video in which the robot jumps and stays in the air as long as possible. So at the end of week 3, they're proposing to achieve what they want, which is a jumping robot. The fourth milestone mentions preliminary A/B testing. So at the end of the 4th week, at the end of lectures, that's when you're going to be submitting these 4 milestones. There's then going to be a gap between end of lectures and the exam period for this class. During that time, you're going to be letting your computer run what's known as an A/B test. You're going to be running 2 slightly different versions of your code base, version A and version B. And we're going to be looking in those 2 versions of your code whether things are easier or harder for the evolutionary algorithm. The idea is to put something into your code that makes it easier to evolve the thing that you want. In this case, the student is after jumping, and their idea for their A/B test is to modify simulate.py again to write out the robot's horizontal distance along with its touch sensor data. And now compute fitness as d times t. So they're modifying their fitness function to select for what behavior now? When we watch all the final projects during the exam period, this is going to be the Robot Olympics. What event are they competing in? This is the long jump, right? So d times t, move as far to the right as possible and maximize a time period in which all 4 feet are off the ground. This will involve long jumping. I'll compare, this is the A/B test, I will compare whether evolving a standing jump, which is what they had at the end of week 3. So at the end of week 3, they have version A of their code base. And at the end of week 4, they have version B of their code base. A, standing jump, B, long jump. And they're going to then compare the results from those 2 versions of their code to determine whether evolving a standing jump or a long jump causes the robot to jump as high as possible by comparing the maximum z coordinate reached by the robot. So in this project, they're interested in jumping all together, but they want to see whether evolving for different kinds of jumps leads to bigger jumps, maximizing the z coordinate. So does the evolutionary algorithm that evolves the long jump, does this make things harder on the evolutionary algorithm because it has to maximize d and maximize t? Compared to version 1, which just has to compared to version A, which just has to maximize t? Which one of these 2 produces bigger jumps overall? That's an A/B test. A/B testing exists in all the engineering branches of engineering, including software engineering. So whenever you land on Amazon.com webpage, unbeknownst to you, there's slightly different versions of the page that you're looking at. And Amazon is looking to see version A, version B, version C of their website. Which one is better in what sense from Amazon's point of view?
Gets you to buy more
Gets you to buy more stuff, right? A/B testing is everywhere. We're doing a similar thing here. Which slightly different version of your code base evolves ultimately for the thing you really want? Big, high jumps. Make sense? Questions? Okay, all right. Okay, so let's look at the timeline. So next Tuesday by 11:59 p.m., what are you going to be doing? In the subreddit, there's a housekeeping section. So you got a relatively big code base here, and we've been going at a pretty fast clip. So there's a couple things you have to go back and clean up in your code base. You're going to do that first, and then you're going to complete your first milestone, which is to describe the 4 milestones. This here is the hypothetical student's first milestone. They're going to put all of this text into the submission for milestone 1, for weekly deliverable 1, and they're also going to do this little bit of work here. Okay. You'll see in Brightspace, I'll make a stub for milestone 1 when I get back to my office. Okay. Copy and paste the text description of your selected project, which for this student would be this. Your 4 milestones, and a link to the image video proof of completion of milestone 1. You don't need to prove to us that you completed the housekeeping section. It's just some housekeeping. Just make sure you do it. Okay. Okay, same thing then, 2 weeks from now, in Brightspace, there'll be a milestone 2 submission stub, copy and paste your text descriptions of your selected project back in for us. We're not going to be able to remember what everybody's working on, and you might include a sentence or two saying, as you'll recall last week, I managed to write out all the touch sensor values in a matrix. This week, you can now see that I'm evolving something to minimize touch. And you can see that in the robot. It's now tap dancing, that kind of thing. Okay, same thing for milestone 3 and milestone 4. Any questions about the 4 milestones? No? Okay, so that'll take us to the end of the lecture period. I mentioned there's a bit of a gap. And then by 11:59 p.m. on the night before our exam period, you're going to be submitting a short written report and an oral presentation slide deck to us, summarizing the results of your A/B test. And then on May 7th, we will all be back here together in person. There will be no recording. We have to do all this in MeetSpace. And you're all going to present the results of your work orally for 2 minutes and 30 seconds. The shortest oral presentation you'll ever give. Okay, we'll talk about the written report and the oral presentation later. You don't have to worry about that for now. We're going to focus on the 4 milestones. And then how are we going to grade this? Your final project overall is 30% of your final grade. 4% for each of the 4 weekly milestones, which sums to 16%. The remaining 14% is for your oral presentation and your written report. 7% for the oral presentation, 7% for the written report, which we'll talk about later. All right, a lot of information to throw at you, but just so we're all on the same page, literally and figuratively. Good? Okay. Have fun. Here's the week to be creative, be ambitious, think big, but be ready to break it down into 4 digestible weekly bits. Okay. All right. Back to the schedule. I called these weekly reports, but let's call these milestones. I think that's a little bit better. So we'll refer to M1, 2, 3, and 4. You can see next Tuesday, there's M1 for everybody. Okay. All right, back to lecture material. We started in on swarm robotics last time, and the intuition here is for a lot of real-world problems, we're going to try and evolve or design or train machines because whatever the task is we want the machines to do, it's beyond the ability of any one big complicated machine. We're going to try and create a swarm of simpler machines. We're looking at a classic paper in the field that goes back 30 years. In which the investigators chose to evolve a swarm of robot lions that are going to chase a robot gazelle around in a virtual Serengeti plain. Remember, we have this sheet of paper. We've rolled the sheet of paper so that the two long ends touch, and then we've rotated that tube so that the two ends of the tube touch, and we've got a giant donut or toroid, and the virtual gazelle and the 4 virtual lions are running around on the surface of that toroid. We're going to use an evolutionary algorithm to evolve the controllers for the 4 lions. The gazelle's behavior is fixed. The gazelle is always going to run away from all 4 lions, and it's going to run away more, or it's going to alter its heading more based on the closer lions. That's where we got last time. Okay, so we're now going to look at the controllers that are going to control the lions, and then we're going to look at how those controllers were evolved. In this case, back in the 1990s, this was still the AI winter, and neural networks were not that popular at the time, so they did not use neural networks as controllers for the robots, for the lions. They used something else, which is genetic programming. And we actually saw genetic programming earlier in the semester when we were talking about different evolutionary algorithms. So, genetic programming is the evolutionary algorithm that they used here. I misspoke. It's the evolutionary algorithm that they used. They're going to use trees to encode the controllers for the robots, and they're going to use genetic programming to evolve populations of trees. Okay, apologize for the small text here. In building controllers for trees, building controllers for lions out of trees, they define a whole bunch of different kinds of operations listed here on the left. And for each of these operations, they list the number of arguments that are required. So as always, when we're running an evolutionary algorithm, we usually start by creating random controllers for our robots. So how do we create a random controller for a lion where that controller is encoded as a tree? We throw all of these operations into a bag, we shake up the bag, and then we pull one of these operations out of the bag at random. Let's assume that we pull last, the operator at the top of the list there, out of the bag at random. Last returns a vector, which is 1 unit, is a vector of length 1 in the direction the lion went last. When we drop this controller into a lion and start the simulation, at the first time step of the simulation during the first move, this node is going to return a random vector of normal length 1. Okay. So we've randomly created this controller. We have 4 lions. So let's assume that we're going to start simple. We're going to take this controller and drop it into the 4 heads of the 4 lions. The lion pride, they're all going to be executing the same strategy, this strategy. All right, we drop this controller into the 4 lions. The gazelle is going to do what the gazelle does. What happens in the simulation? How does the gazelle and the lions run around on the surface of the toroid? How good a strategy is this?
Won't the lions just go in a straight line because they're following their last position with no change?
They're all going to move randomly first. In the first time step of the simulation, they all move randomly. The gazelle reacts and moves away from the lions. And then the lions continue moving in a straight line on the toroid. What happens? Are they going to capture the gazelle? What would happen if 4 real lions just ran off in a straight line? Not very successful, right? Again, not surprisingly. If we create neural network controllers for our robots and we set random synaptic weights and drop that into the robots, same thing, not very successful. Okay. Let's try something else. Let's shake up our bag again, and in this case, let's assume that we pick out addition at random. Addition takes 2 arguments, so we need to create 2 subtrees underneath, and we need to sum 2 things. So we put plus back in the bag, shake up the bag again at random. In this case, let's assume that we pull out random direction. In this case, random direction takes no arguments, so we're done there. We need to fill in something here. We reach back into the bag, we shake it up, and in this case, we randomly pull out gazelle, which also takes 0 arguments. Okay, we take this controller, we make 3 copies of it, and we drop these 4 identical controllers into the heads of the 4 lions, turn the lions back on. What happens? How does this lion pride do? Better, worse, the same?
Slightly better, but because it's got the direction of the gazelle, but still not quite ready because of the random vector.
Because of the random vector. What are the lions doing? This is the genotype. What's the phenotype? What's the behavior that's produced? How do the lions move around on the toroid?
They're going to move randomly, then towards the gazelle, and randomly, kind of just repeating that.
We're actually summing these 2 vectors. So in the controller, we're now dealing with vector operations. So at every time step inside the head of every lion, the lion executes that controller. So it starts by generating a random 2D vector, because we're moving on a 2-dimensional surface. We return that 2-dimensional vector up here. We get this 2-dimensional vector here, which is the vector, the smallest vector from that lion to the gazelle. And we sum those 2 2-dimensional vectors, which gives us back a 2-dimensional vector, which is the direction that the lion moves in. So all of the controllers inside the heads of the lions are performing vector operations. Okay, how are the lions moving?
They're going to go in like the general direction of the gazelle, but like not directly at it.
They're not going to go directly at it. They're going to kind of move towards the gazelle in a random way. Better or worse than the lion pride that was executing this behavior? Better? You sure? Put yourself in the shoes, in the hooves of the gazelle. You're a prey species. There's several predators out there. They're all doing the same thing, and they're all coming at you more or less directly. Not quite, but kind of randomly. Great, right? They're all going to start to move towards you. You move away. They're all a little bit further behind you because you move faster, which means they're now chasing you from behind. Excellent. All of the lions are going to generally converge behind the gazelle, which will easily keep far ahead of the lions because the gazelle moves faster. This is actually worse than this. It's kind of counterintuitive, which is the point. It's actually not obvious what the lions should be doing. Okay. Let's try one more, just to solidify our intuition about what's going on here. Let's reach into the bag and we choose if dot product. This is a complicated one. This takes 4 arguments. 1, 2, 3, 4. We need to fill in a whole bunch of things down here. I'm going to just go a little bit faster now. Add a random vector to gazelle like we had before. Invert a random vector. Multiply by 2. The last direction you moved in, multiply by 2, multiply by 2, multiply by 2. Let's see, gazelle in here. Getting tired of writing, so last direction you moved in and random vector. Here's another controller. We copy this 3 times and drop these into the heads of the lion. What does this lion pride do? You should all know me enough by now. Who knows, right? It gets very difficult very quickly. It's going to be very difficult. First of all, it's going to be difficult to devise in your head a good strategy for the lions. Not so obvious what 4 lions should do, chasing a gazelle on an infinite toroid. Second, even if you could think up what that is, how to actually construct a controller that produces that desired behavior, super hard. So let's be lazy and do what we always do, which is evolve controllers for the lions and the fitness function for the lion pride. The group as a whole, not an individual lion, is going to be what? This is the easy part.
Catches the gazelle.
Get as close to the gazelle as possible, right? In your code base, you've been maximizing horizontal distance. Now we're going to minimize distance between the lion pride, or maybe the closest lion to the gazelle, and the gazelle. So we could start, now that we're going to start evolving populations of these controllers, by creating a population of random trees, random gazelle, plus times 2, ... So we have a population of randomly generated controllers. We evaluate each controller by allowing it to control the pride as a whole and assign a fitness value to it. This particular controller got the closest lion within 3.2 length units of the gazelle, whatever length units mean on this toroid. This one got a lion within 1.7 units of the gazelle. As always, we delete the poorer performing members of the population. When I say population, we're talking about the population of controllers. When I say pride, we're talking about the group of lions. Okay. The surviving controllers, we make randomly modified copies. So if you'll remember from our discussion on genetic programming, we take this tree, for example, and produce a copy. This one survived. It gets to produce a randomly modified copy of itself. We copy some of it, and as we're copying, suddenly there's a mutation that occurs. We delete what was in there before, and we replace it with some selections from the bag again. Question?
In a simulation, are we giving all of the lions relatively the same, brain, and then they're, we're doing that, or are we giving each lion a different one and kind of combining simulation?
Great question. Not relatively the same, exactly the same brain. They are all running exactly the same controller. Does that mean they all move in the same way? So they can still move differently, but they're all executing the same strategy. What you mentioned could be an advance on what we're going to do here, which is allow them to have slightly different underlying strategies. But for now, they're all running identical strategies. Yeah? Okay, so we mutate into something else. This child, which is G plus G, is slightly different from the parent, which is R plus G. Probably this pride is going to have a different behavior, may do better or worse than the parental controller, and around we go. From the perspective of the evolutionary algorithm, which in this case is genetic programming, things look pretty much like what we've done before. So far, so good? Okay. Okay. Are the robots sensing here? Where's the sense, think, act cycle given these controllers?
The only one is the gazelle input.
So lions that are being evolved with these strategies, they only see the gazelle. They don't see their pride mates. They're the lions are at a speed disadvantage. They're also at another disadvantage, which is how do you coordinate with your teammates if you can't see them? So we're going to see some results for this experiment. The investigators conducted a second experiment, experiment B. Let's call this experiment A. This is experiment B. So they're doing A/B testing, which we just talked about. And as always in A/B testing, they're creating these two slightly different experimental variants to see whether A or B produces the thing they're ultimately interested in, which is finding a controller that allows the pride to bring down the gazelle. Yeah? Okay, so what change did they make in version B? Version B is identical, experiment B is identical to experiment A. They're going to use genetic programming to evolve populations of trees that are constructed from this bag of operations. In experiment B, they're going to throw in 4 additional operations to the bag. There's 4 new things that the lions can do. And they're all based on expanding the ability of the lions to sense their teammates. How are they going to sense? They're going to sense using what's called deictic sensing. Deictic sensing is when a machine or an organism senses its environment and it senses things, or in this case, my fellow lions, relative to myself. So when I look out at you, there are some of you that I see that are on my front right, and some of you that I see that are on my front left. I'm sensing you relative to myself. That's deictic sensing. Okay. So the first new operation is nearest, which, as it says, returns a vector from the lion nearest the gazelle to the gazelle. Okay. The next one is lion, which is a vector from the current lion that's running this program to its nearest neighbor lion. Let's think about this controller for a moment. What would happen if we dropped this identical controller into the 4 lions and turned on the simulation? What's it going to do now? What's the pride going to do? Not a great strategy, right? The gazelle's very happy about this one. RL, the rightmost lion, which is a vector. When I'm the lion and I execute this node returns a vector from me to my first neighbor lion encountered in a clockwise loop, which in this case is Bharat. He's the first student I see when I do a clockwise sweep in the direction that I last was heading. So there's my fellow lion. That's a head into the front, to the right of me. L lion is going to return a vector when I start with my heading vector and I start sweeping counterclockwise. First student I see counterclockwise, that's my left-hand neighbor. Right-hand neighbor, left-hand neighbor. That's deictic sensing, relative to me. Strictly speaking, this one, the vector from the lion nearest the gazelle to the gazelle, is not deictic sensing. This has nothing to do with me. This has to do with the lion that's closest to the gazelle. There's a little bit of a mixture here, non-deictic and deictic sensing. How do you think the lions are going to do, how do you think genetic programming is going to do at evolving strategies for prides that are capable of deictic sensing? Are they going to do a better job of bringing down the gazelle compared to evolving prides that can only see the gazelle? Seems likely, right? What? What is the pride going to do? What's a good strategy here? You might not be able to dream up the optimal strategy, which is very complicated, but what's a general good rule of thumb? You're a very hungry lion, and you got 3 other lions, and you can all see where each other is more or less relative to yourself.
Keep each other semi-spread out so you're covering more area.
Exactly, right? So I see Bharat is my our lion here. He's in front and to the right of me. Remember the boids? I'm going to kind of turn to the left and head off this way. I also have a neighbor that's over here. I'm going to try and spread out and move away and hope that my L lion and my R lion are also moving apart. You can use deictic sensing to try and move apart and see whether your fellow lions are doing the same thing. Basically, spread out around the toroid. It's a good start. All right. That's option A, option B, experiment A, experiment B. Anything else we can do to give genetic programming a leg up? No pun intended. Is there an experiment C waiting in the wings? If you ever played a team sport, usually if you're doing it well, you're doing something other than just deictic sensing.
I mean, he in the back mentioned earlier, but like giving them a different controller so they can kind of evolve different roles to be achieving different goals. Like one chases it while others try to cut the line off or figures out.
So we're talking about the evolution of coordination. Typically, for sophisticated coordination strategies, specialization in some way is a good way to go.
Can you say communication?
Communication, absolutely, but we're deliberately holding off on that until the next lecture. We're going to see how well the lions can do without roaring. They're not allowed to make any sounds yet. Also, probably not a good strategy for the lions. They're generally trying to stay quiet, the real ones.
Could you evolve the start location of the lions?
You could evolve the start location of the lions, but that's kind of cheating, right? Lions can't really teleport, as far as we know.
There's no real way to like really implement planning, so is there a way that you could, without using like the CTRNN, use like the last positions to kind of predict where the future predictions might go?
Excellent observation, right? The lions, given these operations, are not capable of prospection, which we've mentioned a few times in this course, the fancy term for being able to plan ahead or visualize what's going to happen in the next few time steps, right? The lions are not capable of that. We could imagine an experiment C in which they allow the lions somehow to prospect. There was a mention of specialization. That's what you're going to see now in experiment C. So in experiment C, they started with experiment A, this base set of operations, and instead of throwing in these 4 additional operations, they threw in these 4 additional operations to the bag, which is operation L1, L2, L3, and L4, where L1, that node, L1, wherever it appears in a tree, returns a vector that connects the current lion to lion 1. So if each of the 4 lions is running this controller in its head, what do the lions do? What does the pride do? How do they move?
Just move on the initial position of the first line.
What does L1 do?
Nothing.
Nothing. Stays still, right? The vector that connects lion 1 to lion 1 is the null vector. So L1 doesn't move. The other 3 move towards L1. Yeah? So now we have specialization. Everybody's still running the same program, but there's the behavior is specialized. L1 is doing something clearly different from the other 3 lions. Okay. Let's think about experiment B compared to experiment C. For which of these 2 is it easier for the evolutionary algorithm to evolve strategies to bring down the gazelle?
Probably C.
Okay, maybe. It's not really so obvious, right? It's getting tricky. It's still a relatively simple experiment. Coordination is tricky. It's a simple experiment, but it's going to get a little more complicated. We've got A, B, C. We're now going to see D, E, and F. Ready? Here we go. Okay, somebody mentioned this already. Cloning controllers is kind of a dumb thing to do, or at least it's very limiting to the lions. Even if specialization is possible, they're still all running exactly the same strategy in their heads. So it'd be nice to have strategic specialization as well, where different trees are running in the heads of different lions. So what we just saw is one possible way to evolve teams. We take one of the trees out of the evolving population, make 3 identical copies, and drop those 4 clones into the heads of the 4 lions. In another experiment, they allowed what they called free breeding, which is they now evolve trees in the population that look like this. It's a little confusing because we just saw L1, L2, L3, and L4. On this slide, L1 represents, I'll draw it for you here. L1 is the root node under which the controller for L1 sits. So the upper node at the top is always empty, and there are always 4 subtrees where this is the tree that's going to be dropped into the head of lion 1. This, for example, is the controller that's going to be dropped into the head of lion 2, and so on. So each tree, like up here, still encodes all the controllers for all 4 lions, but the 4 lions can now be executing different strategies. Okay, what are we seeing here? What we're seeing is, again, when some of these trees are killed off because they produce poor behavior for the pride, some of these trees get together. In this case, there's 3 parents, and each one makes a randomly modified copy of one subtree and copies it into some other subtree in the offspring. So this offspring is a genetic combination of these 3 parents. This offspring inherited lion 1 strategy from lion 2 strategy in parent 3. This offspring inherited lion 2 strategy from lion 1 strategy in parent 1, and so on. That's free breeding. This is a little bit problematic. Why? It's simple to implement. We're allowing specialization.
Couldn't they all just end up with the same specialization?
They might. Imagine inside these subtrees there is an evolving strategy in which lion 2 chases the gazelle, and the other 3 lions, 1, 3, and 4, move away from lion 2, but slowly, maybe random, with a little bit of randomness and a little bit of gazelleness, they start to move towards the gazelle and away from L2. What happens if this child now inherits what was L2 is now L1, what was L3 is now L4? What's the problem here? The parents might have survived because they're starting to evolve versions of this good strategy. L2 goes on the offensive, and L1, 3, and 4 go stealth.
Seems like it's going to kind of just jumble up their roles and make it do a little bit of everything, which is going to make it do worse in the end.
It's absolutely going to jumble things up. So even if such a good specialized strategy starts to evolve in the population, it's going to get washed out very quickly by the fact that everybody's providing genetic material willy-nilly. So the last experimental variant we're going to see is restricted breeding. So assume these 3 parents survived. Actually, 4 parents, I just didn't have room to draw it. Parent 1, 2, 3, and 4. These 4 parents together construct one offspring, where in that offspring, L1 inherits L1 from parent 1, L2 inherits L2's strategy from parent 2, and so on. So whatever L2 is evolving to do, it's going to do something very similar in the offspring. There may still be some mutations that hit L2, so L2 in the offspring might do something a little bit differently than what L2 did in the parents. But we're now not jumbling things up. We're providing the supports for specialization, assuming specialization starts to evolve. Question?
This is only going to create one offspring, though, so how would you create the next?
How do you create the next offspring? So imagine we have a population of 100 of these kinds of trees. 47 of them are killed off. We got 47 slots to fill. We just filled one of these slots. How do we fill the next one?
Could you reduce the restricted breeding so it's like you're only selecting 2 offspring, bringing that over and then evolving it the way you normally would so you get more combinations?
Possibly. It's a good idea. It's a little complicated.
You just shift all the indexes, like, and wrap them around, right? So like this one is giving 1 this time, it could give 2 the next time, and then that one could give
Absolutely. We could create a second offspring where this parent donates L2, this parent L3, this parent L1, and this parent, L4, this parent L1. Even simpler, we could just randomly choose another 4 parents among the survivors and do exactly this thing again, which is what the investigators did. Evolutionary algorithms and robotics people tend to be lazy, right? Do the simplest thing first. Okay, I've lost track of how many experiment variants we have. Luckily, the investigators pulled all this together for us. Let's now look at some results. So they conducted genetic programming 1,200 times. Okay, so a lot of compute. The first, they did 100 runs, 100 independent evolutionary trials, 100 independent evolutionary runs of each of the 3 ways of sensing. So they evolved prides that sensed like this. They evolved prides that sensed like this. They evolved prides that evolved like this. And combinations with the 3 team construction methods. Team construction method 1, method 2, and method 3. So 3 different ways of sensing, 3 different ways of producing offspring, which gives 9 possible experiments. A, B, C, D, E, F, G, and so on. Everybody see that? So they're going to look at all combinations of the ways of producing offspring and the ways of sensing. And for each of those 9 different experiments, for each one, they're going to do 100 evolutionary runs, which gets us to 900 evolutionary runs. That gives us 300 still to explain. The 900 through 1,000th run, they just evolved behavior for 1 lion, so no pride. The 1,000th through 1,100th run, they didn't actually do genetic programming at all. They just generated a random tree, not even a random tree. They just had 1 lion move randomly 100 times. Those are the 100 runs. And they did a final 100 runs of 4 randomly moving lions. Why did they do these additional 300 experiments?
to see if the algorithm really accomplished anything other than just moving randomly.
Exactly. To see whether the genetic programming is actually able to evolve good strategies at all. So these are their control experiments or their baseline experiments or their null experiments. And the scientific discourse, control, null, baseline, all means the same thing. It's if these things actually aren't working at all, they should produce equally efficacious prides to these. These are our baselines. Okay, everybody understand the experimental design now? Okay, off we go. For each one of these runs, they evolved the population for 51 generations. They used a population size of 500, so they had 500 trees in the population at any given time. And as you might imagine, through crossover and mutation, these trees can actually get very, very, very big. So there's a cap. No new trees can ever be bigger than 70 nodes, and they can never reach a depth greater than 17. These seem like ridiculously arbitrary numbers. 51, 70, 17, 500. Genetic programming goes back to 1992, so it's been around for a while. In the very first book published by John Koza, the inventor of genetic programming, he randomly picked some parameters for his genetic programming algorithm. 51, 50, 70, 17, and guess what? Everyone's copied those numbers ever since. They're not necessarily good numbers, they're just the numbers. Okay, all right. Here's some more arbitrarily chosen numbers for you. Most of the new trees are produced by crossover, some by mutation. Okay, I think we've already said this. We're going to place the gazelle and the lion randomly. And, oh, sorry, I haven't said this. So there's only 15 time steps in each simulation. But remember that in this simulation, there's a vector that dictates where the lion and the gazelle is going to be at the next time step. So there's quite a bit of motion. It's not a physics engine. They don't have legs. They're not galloping or pronking around. It's very abstract. So each move lasts 15 times. And the fitness function, which we've already guessed, is be closest to the gazelle. The fitness function actually says the pride wins. It gets a fitness of 0 if any one lion in the pride is less than or equal to 1 length unit away from the gazelle at the end of the simulation, at the end of the 15 time steps. Otherwise, it's this. It's basically get close to the gazelle.
So once the lions can catch the gazelle, does it stop evolution, or would it take into account like how quick it can then catch the gazelle?
Good question. The former. So just did genetic programming capture the gazelle or not, and how close did it get? That's what we want to see, right? From the point of view of the gazelle, once a lion is less than 1 unit away, that's it. We're done. Okay. All right, here we go. These are the results. They don't look very sexy, but we'll walk our way through these tables. Here's the 3, 1, 2, 3. Here's the control or null results here. And here's 1, 2, 3, 4, 5, 6, 7, 8. Here's the 9 experimental variants. Let's start with the control results. There's a number of observations you can draw from this relatively small set of results. The first one, maybe, which is not so surprising, is a single moving random lion and a single evolved lion. These numbers are statistically insignificant. They're very close to one another. So there is no point in evolving controllers for a single lion. There's just nothing you can do on a toroid in which there's no obstacles or no ledges for the lion to trick the gazelle to go off. Nothing. Okay. The 4 random lions actually do a better job. Random. Why? That's it, right? They're moving randomly. So on average, they're covering the 4 quadrants of the toroid. If you unroll it back into a rectangle, they're more or less spread out. There's less places for the gazelle to run, right? It's actually boxed in a lot of the time by these lions that are ignoring the gazelle. So can we do better than 4 randomly moving lions? Look at the 9 results in the upper table. Yeah, it turns out that there is. All of these 9 numbers, let's just look at the averages. They're a little bit more trustworthy. They're all significantly lower than randomly moving lions. So in all 9 cases, even in the most restricted or most constrained prides, which are the prides that are all running identical controllers, and they're all running identical controllers, and they can't even see the gazelle. They're doing better somehow. I love this paper. It's a classic in the field, but it's also a heartbreaking paper because they never show what the actual strategies are. If any of you have some free time, I would love it if somebody re-implemented this experiment. We could actually see some lions chasing some gazelles on a toroid. No one's taken me up on that yet. Okay. 4 lions do better than 1 lion, evolved a random in the control. Let's make some observations among the 9 experimental variants first. An interesting result is if we look at clones, name-based sensing, where is name-based sensing? Here. Name-based sensing for the clones was worse than deictic sensing. So we're looking at 2 experimental variants in which the lions are all running identical controllers, But the ones that had name-based did worse than the ones that had deictic sensing. Why? This is just to build up our intuition for what's going on here.
Is it because the name-based is more specialized for, or ideal for, specialization of different tasks, and if you're giving everyone a clone of it, you can't do specialization in that case?
Exactly. So let's think about the name-based clones for a moment. Name-based meaning somewhere in those controllers there's something like L2 or L4. Do something relative to L2. L2 is being called out as a specialist. What if you are L2, right? Do something relative to yourself, okay. Everyone else is doing something relative to you. It's not great. Why does deictic sensing do better in this case? Some strategies that may be working in here is turn to the right when someone on your left is very close to you. You remember the Bratenberg vehicles, the coward, always move away from things that... It's relatively easy with deictic sensing to evolve things that are like Bratenberg vehicles. I don't want to be close to my fellow lion because that makes things easier on the gazelle. Generally, we should spread out. So if everyone is running the same strategy, always move away from your left hand, always move to the right, away from your left-hand neighbor. That's a good strategy. That means everybody spreads out. Okay. For restricted breeding, where's restricted breeding? Here. So this is where the strategy for L1 gets passed down as the strategy for L1 gets passed down. That gives genetic programming the ability to refine the behavior for a specific lion. It doesn't get mixed up with the other lions. So for restricted breeding, name-based sensing was the best. And in fact, name-based and restricted breeding was the best experiment out of all 9 experiments here. Had the lowest average. Prides evolved under these conditions, repeatedly evolved to bring down the gazelle. Again, we don't know exactly what strategies evolved, but hopefully you have an intuition enough now for this experiment to make a guess at the general strategy.
Not to answer that, just have
Okay,
a question.
sure.
If the fitness isn't normalized, I don't have a sense of like, is 1.33 getting the gazelle some,
Yes, okay, hard to say. So the sheet is a 15 by 15. So this is going to be a little tricky. We're going to try and see if we can figure out what a length unit of 1 means here. So 15 by 15, we turn it into a toroid. The gazelle always moves 3 units away from the lions at every time step. Despite that distance that the gazelle can travel in 1 time step, on average, at the end of these prides, there's a lion within 1.33 units of the gazelle. So it gets within 1.33 units, and then the gazelle jumps away. On average, but there was, in some evolving population here, there was a lion that got within 0.03 length units of the gazelle before it hopped away another 3 units. I think the hopping days of the gazelle are over at this point. Yeah? So yes, the lions are doing very well in this case. Why is this such a successful strategy? Again, if you're familiar with team sports, there's some good precedents here. Any large-scale coordinated task that humans conduct actually is really a kind of a version of this.
The lions specialized, and they found they evolved to have roles that would allow them to chase the gazelle into a way where one could actually get close.
So there's the evolution of specialization, and it stays. It doesn't get washed out. So whoever the specialists are, presumably they're getting better and better at whatever they've specialized to do. We don't know what the specialist is actually doing. There's probably one that's on the offense. That's the one that chases the gazelle, and the others do something else. So there's the evolution of a division of labor. And then that ability gets better and better over time. Inside the lion pride, they quote unquote know who the specialist is and what that specialist is going to do, generally speaking. They don't explicitly know it. They cannot just sense their fellow lions and how those lions are moving and how the gazelle is moving, but they are evolving division of labor. Okay. That concludes our discussion of coordination. Any other questions about this experiment before we move on?
Yeah, the restricted breeding isn't like that much better than the cloning. Is it significantly harder to compute or like harder to implement? It seems like the cloning would be easier and works almost as well.
It's almost as well. Almost as well. So it's kind of diminishing returns here, right? So again, this is on the toroid, things are very simple. So there's still some advantage to division of labor, but it's probably not much. Now, if we made the toroid bigger, we threw in some obstacles, everyone had limited range of vision. Remember the boids that could only see so far? My guess would be, and it's just a hypothesis, that now this would start to have a greater advantage over the other 8 experimental variants, possibly, right? The more complicated things become, the greater the pressure to specialize and coordinate based on specialization.
Just looking at, I assume the average is taking in like all of the runs even when it's randomly generated?
Sorry, I didn't explain the averages. So remember that in each of these 9 experiments, they did 100 evolutionary runs. Across those 100 evolutionary runs, they plucked out the best pride at the end of that run, and they had 100 champions. And this is the average behavior of those 100 champion prides. This is the best of those 100 champion prides. Thanks, I forgot to mention that. Any more questions about that? Okay, hopefully at this point you're feeling the lion's pain, right? They're trying their best. They're trying to evolve specialization. They're still kind of hungry, right? They're still not doing a great job. There's only so much they can do by looking at how their fellow lions are moving.
Now that the averages are explained,
Yep.
it'd be interesting to see like you take like the couple best prides and then run those to then pick which one you're actually evaluating, because the best pride could have just been like randomly better than the rest. If the others had had more run time, they would have done better, seeing that it was able to get that low, and maybe you could find when they got closer.
Possibly, right? Evolution is a satisficer. This is not necessarily the optimal, right? There might be even better controllers out there. We just don't know. Yep, good observation. Okay, so again, I'm kind of feeling bad for the lions here, right? They're doing the best they can. If only they could say, I'm going around the gazelles to the gazelle's left, and they're speaking in a way that the gazelle can't hear, right? Very important, right? If you want to coordinate at scale, there is increasing pressure to not just coordinate, but communicate. Okay, I've held off on this for a while. So we've got 5 minutes left, so we'll just start in on the evolution of communication. My apologies, I didn't put up the link to this slide deck until this morning, so bear with me. Okay, so we're now going to look at another simple experiment, no more lions and so on, where now the agents are capable of communication. Communication is super helpful for obvious reasons, but it's also very difficult to evolve. We are capable of explicit language. There are few other species on this planet that are capable of explicit communication, but not that many. It's actually very difficult for Mother Nature to evolve communication into a species. Why? Super helpful. Hard for evolution to find it.
Can you clarify what you mean by explicit communication?
I'm saying something and it's causing vibrations in your inner ear, which is changing electrical impulses in your brain, which maybe will alter your behavior at some point in time. There's sound waves that are going, and you can measure the amount of information in it. There's certain things that I can say that if I say them again, a short time later, you're going to do the same thing.
I guess I'm thinking of like ants leading other ants to the spilled lemonade. Or
Okay, so you're talking about stigmergy. So absolutely a valid form of communication. I'm an ant, I'm walking around, and I find a huge pile of sugar. Somebody dropped some sugar in the kitchen. I turn around and go back the way I came to the nest, and as I do, I drop chemical signals on the floor, which contains information. It says, follow this trail, right? So stigmergy is absolutely a form of explicit communication. What about in the lions we just saw? There's no explicit communication there. They're not dropping chemical trails for their fellow lions to follow. They're not sending out compressive vibrations through the air. That's what I mean by explicit communication. We can do it, ants can do it, other insects can do it, certain other mammals can do it. Really, really big mammals figured out that water is actually a wonderful conductance for long-range communication. They figured it out. Again, not that many. Why? Why is the evolution of communication so difficult?
You have no way of communication and no way to communicate already. It would be hard to then assign meaning between two things to what something is.
Okay, we're getting there. You've got it. What explicit? Can we be more specific?
I was gonna say if you don't live in like a large enough population and you don't have enough like animals to communicate with, then your communication can't really evolve.
Okay, that's true. So you're part of a small population, or your particular strategy or way of surviving is to be off on your own most of the time. So if you tend not to be around your conspecifics, the other members of your species a lot of the time, then yeah, communication's not very valuable. Actually, it's not very valuable in those situations. There's cases where communication would be super helpful but hard to find, hard to evolve.
I'm gonna say like, if a species or like something in the population evolves like a way to communicate, if the other things in the population don't know how to understand it, then mutation doesn't gain a genetic like advantage.
That's it, right? So this is the sender-receiver problem. You mentioned it, right? So English and most other human languages are horrible. There's very little information content in it. Wouldn't it be great if we fixed English to be much more efficient? We could say many fewer things and communicate a lot more stuff. I'm brilliant. I know how to do it. I figured out English Prime. It's way better than English, and I'm going to start using it. Guess what? English Prime never manages to get off the ground because no one understands it. You need to have mutations or changes in a population where there's a change in the form of communication. It could be language, it could be chemical cues, it doesn't matter. But both the sender has to reliably alter the signal that's being emitted, and the receivers have to be able to reliably respond to it in the appropriate way. And evolution has to make those changes through random trial and error, mutation and crossover events that don't break whatever's there already. That's why it's tricky. In the evolution of communication, there's a bit of this chicken and egg problem. You got to get both things right at the same time. Okay, I think this is a good place to pause for today. We'll continue our discussion of communication on Thursday. You're now working on your first deliverable. See you on Thursday.